Hello physics students. In the last video, you learned that any two charges experience a force from each other. You learned the equation called Coulomb's law to determine the magnitude of that force, kq1 q2 over r squared, and you learned that opposite charges attract, positive negative for example, and that like charges repel. Positive positive repels, negative negative repels. But where does this charge come from? That's what we're going to be talking about in this video. Now, I mentioned briefly that one example of a charge was a proton and an electron. And that actually is the basis for all charge. It turns out that charge comes from anything and everything. Your body is made of atoms, which are made of protons and electrons. So your body is a potential source of charge. In fact, it's filled with charge. The chair you're sitting on is also all charge. Of course, there's some neutrons, but there's just an enormous amount of charge in the chair you're sitting on. The air you're breathing, the earth you stand on, every single piece of matter that you touch or encounter is a source of charge. But what we need to do is learn the specific ways that you can accumulate an imbalance. That's the source of this PowerPoint presentation. Also, I have some demonstrations that I recorded in an earlier video for another class. So we'll be looking at those as examples of accumulating charge also. So let us begin. So the first example, I have here an atom, a helium atom. And of course, helium you probably know is a gas. So when we're talking about most of the matter you're encountering on a daily basis is hardly ever helium. But I picked helium because it's simple. It's got two protons you could see here in the middle and two electrons orbiting around and two neutrons which are represented by the gray circles. So I don't want to make it any more complicated by showing like a piece of styrofoam. That would be a very complicated molecule. The point is that in a neutral atom, whatever it is, it has an equal number of protons as electrons. So you see two protons, two electrons. So now, how do we figure out the charge of these things? We can look at our reference table. So front cover tells us the charge of electrons and protons. But if you look through the whole front cover, you will not see a charge on a proton. You will not see a charge on an electron. What you'll see is this one line here called, and it says 1 elementary charge. The symbol for it is lowercase e, and it has a value of 1.6 times 10 to the minus 19th, as you could see right here. So that is the charge of a proton. So if you need the charge of a proton, you need to know that you look up this 1 elementary charge right here. It is also the charge of an electron. The only difference is the number's the same here, but it's negative. So that's where you find the charges of these on the reference table. So let's go back to our helium atom. How do we figure out the charge of this helium atom? Well, this is actually right here. This Q equals Ne is a formula that unfortunately is not on the reference table, but is part of the curriculum. This is the only example of a formula that's not on the reference table. And the logic of it is that charge can either be plus or minus, as you could see here, but also this N is how many protons or electrons you have, and E is that elementary charge of 1.6 times 10 to the minus 19. So if I want to find the charge of this atom, I have N equals 2 for the number of protons here, and each proton here is 1.6 times 10 to the minus 19th. And then I have two electrons right here, and each is negative 1.6 times 10 to the minus 19. So when I punch that in on my calculator, I get the charge is 0. So the helium atom is neutral. But how do I make a charge? How do I charge it up and upset that balance? What I could do is I can add an electron. So this would make a slightly negative situation. Now, one thing I want to point out is helium is a noble gas, so the chemistry is wrong here. It will not accept an electron. Again, this is just a model so we can understand the charging with a simple an atom that shows the process here. So I'm adding an electron to some neutral molecule, like maybe a piece of plastic or your hair or your sweater or something like that. Now how do we find the charge now that I've added this extra electron? I use that formula not on the reference table, Q equals Ne. I have one extra electron here, and each electron is minus 1.6 times 10 to the minus 19th. Now granted, I have 3 electrons total, right? One here, and one here. But these 2 electrons are negated by the 2 protons, so the only thing that matters is the thing that imbalanced is this extra electron up here. So when I punch that on my calculator, well, I don't even have to because it's simple. I get just the charge of that situation is negative 1.6 times 10 to the minus 19th. What if I want to make something even more negative? So you see here more negative charge. I could add 2 electrons. And now, what is the charge of this particular item? Well, I have 2 electrons that are balanced by 2 protons, and again, I'm not even going to consider them. I'm just going to consider these 2 extra electrons here. So my formula Q equals N here, N is 2, as you could see right there, and E is the charge on 1 electron. I punch that on a calculator, and I would get 2 times negative 1.6 10 to the minus 19 gives me negative 3.2 times 10 to the minus 19th would be the charge of that object. All right, so let's suppose I want to make a positive object. So electrons, easy. Negatives, I just keep adding electrons. Now you might be thinking, well, okay, so if I want a positive, maybe I'll add some protons. Well, turns out that is not how you do it. The problem is the protons are inside the atom. And I mentioned this briefly in the last video, that when you rub an object, you're rubbing on the outside, you're rubbing the electrons. You can't reach in to an atom and grab the protons or touch them. So all you could do if you want a positive is not add a proton. They're sort of like inaccessible. But what you could do is you could remove an electron. So as you can see, I strip an electron away here. What happens then? Now this atom, or the object we could say, is missing an electron. And so if you look, with that gone, this proton and this electron negate each other. There's one proton that no longer has a partner. So the charge on the object now, using this Q equals plus or minus Ne, I have one proton here, and each proton has plus 1.6 times 10 minus 19. Again, I have 2, but only one that's not balanced out. So that's all I care about when I'm finding the charge. So when I multiply 1 times that positive number on a calculator, well, I don't even need to do that. I get the answer of this object having that amount of charge. By the way, you're not writing this down. Don't worry about this. I should have said this in the beginning. Too much information. I'll tell you when to write things down. Okay, so let's go on. What if I want to get even more positive? Well, then what I can do is strip even more electrons away. Again, I cannot add protons. So I strip 2 electrons away. Now I'm missing an electron here, missing an electron here. And what that means is there are 2 protons without partners that are unbalanced. So then the charge on this object now is, using that same formula, 2 excessive protons unpartnered. Each one has this plus 1.6 charge. Punch that on a calculator, and you get the charge of positive 3.2 times 10 minus 19th. Again, you're not writing this down. So let's continue. The point is, charge is quantized. That's a fancy word in physics, but what it means is it comes in fixed bundles. For example, these are all charges that are possible in the universe. Anywhere in the universe, you might find charges that are equal to these. Why are they possible? Well, if you have 0 charge, that means you have 0 protons or electrons in excess. But 1.6 times 10 to the minus 19th, if it's positive or negative, that means you have either 1 electron or 1 proton. And you could have that. You could also have this 3.2 value here, because you could have 2 electrons or 2 protons, or 3 electrons and 3 protons, or 4. So you can have an integral number. That's what we mean by it's quantized. It comes in fixed bunches. But what is not possible Here are some examples. There's many, but this is just some example. Why is 8 times 10 to the minus 20 not possible? Because if you were to calculate that out, that turns out to be half of an electron. You cannot split half of an electron. You can only have 1 or 2 or 0, not a half. This is 1.5 right here, which is a little bit less than 1.6. So you can't have 0.9 electrons or 0.9 protons. Cannot do it in nature. This is 1.7, a little bit beyond 1.6. You cannot have 1.1 electrons, or 1.5, or 8.8. So those are impossible. And this is actually kind of popular on the Regents, particularly on a multiple choice question. They ask you, what's possible? And they give you a multiple choice question. Maybe they give you this 1.6 right here, a 3.2, a 0, and a 1.7. And how can you pick out which is impossible? Well, what you do is you go back to this formula, Q equals plus or minus NE. You plug in the charge that they gave you, 1.7 times 10 to the minus 19th right here maybe. The charge 1.6 times 10 to the minus 19th in for E, and you solve for N. If N doesn't come out to 0, 1, 2, 3, 4, some exact whole number, I don't care where you are in the universe, on the opposite end of the galaxy, inside, or on your way into a black hole, doesn't matter. You cannot have a partial number of protons or electrons. So that's charge being quantized. Now, I believe I wanted that copied. Let's see. Oh no, this is what you're going to want to copy. So here's a summary. And I tried to make the bright parts important. I watched a PowerPoint, TED Talk the other day, Death by PowerPoint. This guy gave me all kinds of hints how to make things bright and dark. Hopefully you're enjoying it because I try to put some of this in. But basically the summary, you can be negative only by gaining electrons here. You can be positive only by losing electrons. This formula is how you figure out either the charge or N. E is always 1.6 10 minus 19th, and something I didn't mention yet, charge is conserved. You're going to see that in the next videos. Now, of course, I highlighted these, but copy all of this down. So I will create a pause to give you a chance to copy this down, the first thing to copy down. All right, so let's move on. Now we're going to talk about actual techniques how you can build up charge, because my body and your body and the table and all that stuff, we're all full of protons and electrons, but we're neutral right now. So how can I become charged up? I'm neutral because, as we saw with the helium, I have an equal number of protons and electrons as a balance. So these are the 3 ways to disturb the balance. Again, you don't have to write this down. I'll tell you when you should have to write things down. All right, so here's what's called charging by friction. And it's basically just that, you know what friction, you're going to rub things together. So before, notice, I've got, and I try to draw some atoms here, a proton and an electron. This is like an atom. Here's an atom. Here also, here's an atom. 3 atoms of hydrogen, real simple. And this has 4 atoms of hydrogen. Because they're an equal number of protons and electrons, both things have a 0 net charge. I rub them together. And then watch what happens. There's going to be a little animation here. See these little minus signs? By the rubbing process, they're going to be stripped off. This is supposed to be a piece of fur. And you'll see them move. Ready? Here we go. Oh, there they go. Right there. Right? Now, if you look closely, there are 1, 2, 3, 4, 5 electrons here, but only 3 protons. That means it has an extra 2 electrons. And this has 4 protons and only 2 electrons. It has an extra 2 electrons. So this is how we would express the charge in terms of E, the elementary charge. But if you want it in coulombs, you'd plug in 1.6 times 10 minus 19 in both those locations, multiply, and you get the value of coulombs. Now here's a note. Charge is conserved. Notice I have 0 charge before, right? And then I have, when I add these together, I have 0 charge after. That's true in the universe. Charge is conserved through all charging processes. It's quantized. I already mentioned what that is. And charge is transferred by the movement of electrons. This became positive not by gaining protons, but by losing some electrons and ending up with more protons. All right, so here is, I believe, the summary. This is what I want you to copy, except for the copy into your notes. Obviously, that's a note for you. So again, the key points after rubbing together, the two charges of each, and these arrows indicating that this electron, these came from these protons, leaving them imbalanced, and then write these statements out. So I'll create a pause. Okay, so now what I want to do is send you back in time again, as I like to say, to a time when I was doing some demonstrations for my physics class, electricity and magnetism. So they started right away with charging because that's the whole course on electricity and magnetism. So I'll send you back and I'm going to show just what you can do to develop charge. So hold on and I'll see you in a moment. It turns out that the fur and the plastic have different strengths at which they pull electrons into their molecules. And the plastic has a stronger affinity for the electrons than the fur. So when I rub these two together, what will happen is there'll be charging that occurs. And I don't know if you'll hear it, but, well, I can't really hear the sparking, but, oh, wait, maybe, there we go. All right, so welcome back. I had this plastic rod and I rubbed it with this. It's actually really is rabbit fur. No, I didn't kill the rabbit. You can buy it in a science catalog. So rubbed it, and hopefully you heard the sparking as I was rubbing. So let's go back to our presentation here. And next thing, remember there were three methods of charging. We just discussed charging by friction. Now we're going to discuss charging by contact. So you could kind of guess what that is. You have things that are charged up by just touching, not rubbing. Not friction, but by contact. So you just touch them together. So this right now, this object here has 6 extra electrons before. So that's why we see the charge is negative 6e right here. This has a balance. It may have 1,000 protons and 1,000 electrons balanced. So we say Q is 0 and we don't draw anything because there's no imbalance. Then what happens is you touch them together. And then what happens is there's going to be a little animation. While they're touching, you see how this says 6 minuses over here? Some of the electrons, while they were touched, jumped over to the other object. And now you can see that this has only 3 and this has 3. The notes, again, are that charge is conserved, only electrons moved, and charge is evenly split if the conductors are identical. If one was bigger than the other, we wouldn't have it as simple. But charge is conserved. We have negative 6 before and negative 6 when we add those two together after. Again, you're not copying this. I'll tell you what to copy. So going on to the next one. Well, what happens when one thing is positive over here? Remember, I made that positive by stripping 6 electrons away, and now there's 6 protons without partners. So there's extra 6 protons. When I touch these two together, do the protons jump into the other object? No, I said protons don't move. So this is what would happen. Remember, the other object has a balance of protons and electrons. That's why it's neutral. See, 3 negatives, 3 positives, charge is 0 here. But when you touch, what happens is 3 of those electrons are stripped away and they neutralize 3 protons over here. And so what happens is we have 3 plus 3 on each of these. So again, the electrons went this way, not protons that way. So charge is conserved again. Notice I have plus 6 before and I've got plus 6 after. Even when positive charges are involved, charge is still transferred by the exchange of electrons. And the charge is split evenly if you have identical conductors. So let's go on. So here is what I want you to copy. I did the example of the positive. I don't want you to sketch all the examples, but here's something with +6. As I mentioned, these 3 arrows represent the 3 electrons that moved from A to B, and then they ended up +3, +3e. And then the summary, only the electrons moved. If the spheres are equal in size, they will end up with the same amount of charge, 3 and 3. And charge is conserved, as you could see from this little equation that I did right there. So I'll create a pause to allow you to copy this down. All right, so the next thing I want to do is send you back in time to my previous video. But before I send you, before you go, I want to mention what you're going to be looking at. So here you see a little couple styrofoam spheres. Probably hardly see them because they're so small. And they're called pith, P-I-T-H. They're used in the old days for padding in helmets, I think during World War I or something like that, I forget. But basically, I'm going to be charging these by contact. They're hanging on these little threads, and so that's what you're going to see an example of charging by contact. So, again, let me send you, and I'll see you in a moment. Okay, so it's going to attract and then touch, and then after it touches, notice what's happening to the pith balls from the rod. They used to be attracted. Now look at them, right? So you saw I touched the rod to the pith balls, and then because the pith balls suddenly got some negative from the rod and the pith balls were negative, so they repelled each other. They touched, contact, and there was a charge transfer, both negative now. What I'm going to do is show you another little segment from that day where I then remove the rod, and then you're going to see what happens to the pith balls. So after the rod is gone. So I'll see you in a moment. Phenomenon that we're supposed to see. I guess I'll just tell you, because it's not working that effectively, but basically they are repelling each other now. Okay, now it's working a little bit better. All right, so you should have seen the 2 pith balls repelling each other because they were both negative, because they were both charged by contact. All right, so that was number 2, charging by contact. There's a third charging method, charging by induction. This one's really cool but kind of complicated. So you have 2 metals that are touching. That's step 1. Both of them are neutral. They have an equal number of protons and electrons on each of them. The next thing you do is you bring a charged object over here, but you never touch these. So charging by induction, the charged thing never touches the 2 objects. And what will happen is some of the electrons from this sphere over here get attracted over because they're attracted to that positive, and they leave 4 protons without partners. So now this has 4 extra electrons. This has 4 protons that lost their electron partners. So the charged object brought near, but it never touches the 2 objects. That's step 2. Step 3, what happens is the spheres separate. See how they're touching here? Now I'm going to separate them while this charged object is close, and that's critical. If I were to move this charged object away here in step 2, then these minuses would go back into the positive. But by separating them, I've made them now stuck away from each other. And then the 4th thing that I do is I remove the charged object. The 2 spheres end up charged without ever getting touched. So here we go. There we go. Nice little animation. That's also what the guy in Death by PowerPoint told me. Make things move, and it catches your eyes. So hopefully you could see that. And now what I have here is 2 charged object never touched anything charged. So the summary of that, this is what I want you to copy in notes, the 4 steps written out, and the little note on the bottom. So I'll create a pause for you to do that. All right, now I would show you an example of charging by induction, but not yet. at the end of the video, because there's something that you need to see later in this PowerPoint called an electroscope, and you need to know how that works before you could see that. So let's now move on. The summary, okay? You don't have to write this down, but again, charging by friction, contact, induction. All right. Another term, grounding. And grounding is removing charge by connecting a charged object to the earth. Let's see how that works. So here's something before. It's got 6 extra electrons, so it has a charge of negative 6e. What I'm going to do is connect it to planet Earth, and in a diagram, the way you sketch grounding schematically with like a representation is you draw this series of lines getting smaller. Whenever you see this in a diagram, whether you're looking at your stereo, a circuit diagram of your car stereo, whatever, you'll see these. Engineers put them in the diagram. That means it's grounded, a point that's connected to the earth. This is what it does to these minuses. Let's take a look. Another nice little animation. Here it goes. Watch these minuses. Oh, there they go, right into the earth. And so what happens as a result is this is now neutral because the excess electrons are gone into planet Earth. And so that's grounding. That was an example with negative. What about positives? What happens if I have a sphere that's positive and got connected to the Earth? Do the protons rush into the Earth? You have to, hopefully you're saying, no, absolutely not. We know protons don't move, only electrons during the charging process. So how did this become neutral if only electrons can move? You connect it to the Earth, and the Earth, in addition to being a place you could dump electrons, it's also a place where there are a nearly infinite number of electrons that you could pull up out of the Earth if you want to. So these positives attract electrons in the Earth, and here they come. Oh, there they go. You see them? Well, in case you missed the little animation, I'll show it to you again. I like it. It's fun. Watch the electrons come up. There they are. And they touch all these protons and neutralize, so we don't have plus 6e anymore. We have 0 charge. We had positive, we went to 0. So that's grounding, okay? And here's this thing I want you to copy in your notes. Before, you have plus or minus q. Doesn't matter, positive or negative. When you touch it to the earth, that whatever that charge is now in the earth here, and the thing is neutral after you touch it to the earth. Here's the summary. I chose to highlight that the thing becomes neutral, whether it starts off negative or starts off positive. But write out the whole sentences in your notes. I'm just trying to emphasize, okay? All right, so now what I'm going to do is I am going to send you to the day I was doing all these demonstrations, and I'm going to show you grounding with the pith balls. Remember, I left them charged. I touched them with a plastic rod, charging by contact, and they were repelling each other. Let's see them grounded. Now, I'm not going to connect them to the earth. I'm going to connect them to me, because I'm like big to the pith balls, like kind of like earth is to any other charged object. So enjoy the little demonstration. So you should see these things still repelling, okay? And now keep in mind, I'm much larger than those pith balls, right? I'm like thousands of times more massive than that. So here I come, a big source of charge. And right now I'm neutral, nothing charged me up. And I'm going to come and touch these both with my hand, and then I'm going to let them go. All right, that was fun, right? So let's go on, take a look at the next thing. So now if you look at Coulomb's law, it is, well, I need to get the light on here, so let's see if I can get this to show up. All right, here's Coulomb's law. So F equals KQ1Q2 over R squared. This is on the reference table. If I put one charge here, maybe like, I don't know, 1 Coulomb or something like that, and the second object here is 0, uncharged. Looking at this equation, you would conclude that by plugging in 0 here, multiplying and dividing this out, you get 0 for an answer here. And it turns out that you can have things attracted to neutral objects. Very fascinating thing. And it's called attraction by polarization, which is the next thing we're going to look at right here. So attraction by polarization. Opposites attract, yes. And charged and neutral attract. So let's see how you could possibly attract a neutral charge. So let's take first the non-metal. So what I'm talking about is maybe styrofoam, your hair. That's a non-metal that often gets polarized. You know, when your hair sticks to things, you probably had that experience in the winter sticking to sweaters or something like that. So any kind of styrofoam, plastic, rubber, you know, non-metal, right? So here's the topic, polarization non-metal. Before, this is showing not all the atoms, but only 6 of them, okay? And atoms are made of protons and electrons, and the electrons are orbiting around the protons, as I already mentioned. But let's take a closer look at the pattern here. If you look at these 2 top atoms, you can see that for this one right here, the top one here, the electron is over here, whereas for this atom, it's on this side. In other words, the electron position is random. Sometimes it's on the left of the atom, sometimes on the right. Of course, sometimes top and bottom too. I'm just really simplifying here to see the phenomenon. So then, what that means, if you look at the surface of the metal, right, of the non-metal here, sometimes the surface, sometimes negative and sometimes is positive. So here it's negative, here it's positive. If you look, sometimes we got positive, sometimes negative, positive, and overall that averages to neutral. So the surface of the metal, of the non-metal is neutral. Now what I'm going to do is now a negatively charged object is brought near the neutral object. It does not touch the neutral object. Here comes my little animation. Ready? There it comes in. Nice. Okay. So what does that do? What it does is it repels the electrons in the atoms so that they end up spending more time on the right side of the orbit over here. See this electron right here? The white arrows are showing those electrons. They're repelled from this object. So here comes a little emphasis. Oh, look at those nice arrows growing, showing you those electrons. And then the little animation. Ready? Watch these electrons, these 3 by the white arrows. They're going to move. Here they go. There they go. Nice. They're repelled to the back side of the atom. What does that do? Now, if you look, the protons are closer to this negative 6e. See all the protons here? Because the electrons are back here. So what does that do? The protons are attracted more than the electrons are repelled, because remember, everything is divided by r squared. So the electrons over here are at a bigger radius. That means their force is smaller. And I think I made a little emphasis here. The arrows are going to flash for you. See that? Nice. So what does that mean? Well, let's suppose this is 6 newtons, this green arrow, and this is 2 newtons. The net force there is 4 newtons attraction. And there it is. The net force is to the left, and that means charged objects attract to neutral objects through polarization. All right? Now, I'm going to show you polarization for metal, but first I want to show you polarization by sending you back to the demonstration so you could see how I'm going to attract a neutral pith ball with the charged rod. The pith ball will be hanging down all by itself neutral. I bring the charge rod, you'll see an attraction. 0 charge for the pith ball, negative for the rod, and there's an attraction. So, enjoy. Okay, so, oops, wasn't supposed to touch it, but you saw what happened. Okay, a little. Okay, so let's go on to seeing how polarization works with a metal. So, oh yeah, forgot. You had to copy this into your notes. So let's take a moment, again, except for this little note here. Copy everything you see now. I guess you could draw only 4 atoms if you want, and that would give you the pattern. And you don't need to draw 6 of them. Okay, so go ahead and do that now. All right, hopefully you copied all this down also. So now let's go to the metal. All right, so how does that work with the metal? a similar thing, but even more dramatic. So here's the metal. You see before, we've got this random distribution of the electrons. So that's all this is saying. We don't even need to read it. Same thing as before. This is overall neutral on this side over here. So then we bring the charged object again. Here comes the little animation. There we go. That's fun, right? So what does that do? Well, this repels the electrons not to the other side of the atoms, but all the way to the back surface over here, way back here. So, see them? Oh, well, maybe you missed it. I didn't warn you. See these 3 electrons right here? Right, and there? Watch them go. I'm going to hit go, and they're going to go end up back here. Ready? Here they go. Oh, there we go. Nice. Right there. So, there's a much greater difference in attraction of the protons and repulsions of the electrons. I'll put the arrows in. Look at the flashing, the attraction here. So this might be 6 newtons, and this might be only 1 newton. The net force on this object here is 6 minus 1, or 5 newtons of attraction. And the net force is to the left. And the charged object attracts the neutral metal through polarization. Now this, you don't have to copy because it's enough to do the non-metal. So, you know, that's, I don't want to get too much into that. So the next thing, the electroscope. This is also something popular on the Regents. What is an electroscope? So, let me show you. Uh-oh, it's broken. So, well, maybe it's a good thing I took this apart. So this is the inside of an electroscope, and maybe I'll go back into the light here so you could see a little bit better. So what we have is a metal ball on top, and hanging on the bottom, 2 pieces of metal. Maybe I'll try. Hopefully the light doesn't fall off. Okay. 2 pieces of metal hanging on the bottom. And so they can freely sort of swing around, and then what I do is I put that into something like this flask, this glass flask. And what it does is it detects charge. And so what I'm going to do is send you back to see what happens when I put a charged object near this electroscope. So I'll see you in a moment. And I will bring a charged rod, and you should see that they spread apart, right? So you can see that. All right, so you should have seen those little veins, those hanging pieces of metal spread apart when a charged object was brought near. That's why we call it an electroscope. It detects charge, whether or not objects are charged. But how does it work? Why did those veins spread out? Well, let's take a look. So here we have a neutral electroscope, the essential parts of it. The metal on the top, the metal shaft, and these 2 veins hanging down. These are called vanes, right? So I mentioned that. And the force of gravity pulls them down so they hang. When the vanes hang down, it's not because they're attracted. A lot of students think, oh, they attracted, they came together. No, it's because gravity makes things hang down. That's all. Right? Now, what we're going to do is we're going to take the neutral electroscope and we're going to bring a positive object near. But we're not going to touch it. So here we go. Another little animation. There we go. Comes in the pot. I didn't touch it, right? I just brought it near. What does that do? Why does that make the veins spread apart? So what that means is because this is metal, some of the electrons get pulled and attracted to this positive bar up here. So they get pulled up out of the veins, leaving the veins positive. Ready for another little animation? Here we go. So watch this. See those electrons? They left 4 protons unpartnered. Oh, let's watch it again. It's fun. So here we are, the 4 electrons leaving the 4 protons. So what happens as a result, now notice there's positive, positive near each other. That makes the veins spring apart. The veins repel because they're both positive. But an important point, if this comes up on the test, notice that the total charge on the electroscope is still 0. I have 4 positives here, right? And I have 4 negatives up here. Net charge is 0. Has to be because I never touched the electroscope. I only shifted the charge around. So what I would like you to do is to copy this into your notes. So I'll create a pause for you to copy this down. Okay, again, I hope you made the 4 positives, 4 negatives equal amounts. What happens if I bring a negative object near? Well, no animation here. It's just the reverse. What happened is some electrons here, up here, were repelled down into the veins down here. Now notice I have 4 electrons down here, 4 protons up here. Must be exactly the same amount because I never touched the electroscope. Now the veins spread apart because they're both negative. So here's the explanation. So go ahead and copy the diagram with exact number of plus and minus and the little note there. Okay, so what I'm going to do is send you to look at some more electroscope demonstrations. But the demonstrations, I'm going to use this electroscope here. So again, bad lighting because I'm trying to make the PowerPoint, Death by PowerPoint guy happy. But, well, maybe I'll take this plate off. I think it'll be a little bit better to see what's going on. So this has 1 vein only. And so it's a more dramatic show. Maybe I'll just show you the demo a little bit more back further so you could see. But basically, it works the same way. When this 1 vein goes out to the side, you're just going to know that in a normal situation on a test, we would have 2 veins springing apart. And you would always draw electroscopes like this. So what I'm going to do is show you the demonstration, the same thing I saw. I'm going to bring a charged object near the electroscope, and then you're going to see that 1 vein spread apart in more dramatic fashion. So I'll see you in a moment. Okay, and you see a nice dramatic, right? You see that needle spring out. Okay, so I'm not touching, I'm just bringing that rod near. Alright, so now I'm going to show you another demonstration of what happens when I take this negative away. And I'll tell you first, and then you'll see it in the video. But if I take this negative bar away, okay, what'll happen is these negatives here are no longer repelled away from those protons up here. So they're going to return back up and neutralize. And since the electroscope veins become neutral again, they'll come back together, not because they attracted, but simply because gravity pulled them down. So I'll send you back and observe what happens when I take the charged object away and how the vein collapses. The rod is near, it never touched, right? The veins are spread apart. Now in part 2, I remove the rod. Okay, so the next thing that I want to talk about is what would happen if I actually touched the charged object to the electroscope. So I'll show you first, and then I'll show you that happening with the demonstrations I recorded in the past. So this is what would happen. The electroscope, after it's been touched by a negative object, and what happened because I touched it, it's like a charging by contact. Some of the electrons off that negative object that I touched on the top here jumped into the electroscope. And when I remove that negative object, now you see the electroscope does have a net negative charge, and that's why the veins spread apart and stay spread apart. So the total charge on the electroscope is now negative because it gained electrons. So go ahead and copy that down into your notes now. Okay, so the next thing that I'm going to do, as I said, is send you back so you could observe that happening when I touched the electroscope with a negative object. Getting good charge transfer today. There we go, that's better. Okay, so that was charging by contact the electroscope. I'm going to send you back to see what happens now I'm going to send you back to see grounding occur. So I have this electroscope charged, and then you'll see how I can remove the charge simply by touching it, and I become like the earth to this electroscope because it's so small, and the electrons jump into me and I remove the charge. So that's the next demonstration. Watch me ground the electroscope and return it back to neutral. He then touches the electroscope with his hand and releases it. So here I go, touched it, let it go. Okay, so let's now look at what happens if I touch the electroscope with a positive object. Here I touched it with a negative and made it negative. So let's take a look at that. So what happens here? The title touched by positive, and then I released it, and you see positive everywhere. The veins are spread apart. Oh, there's a typo here. This should say plus plus here, right down in here. You see that mistake, so you could do that when you copy that into your notes. Again, the total charge on the electroscope is now positive because it lost electrons. I touch it with a positive. Positives don't go in. Some electrons get stripped out and go into the positive object, leaving this now positive. So go ahead and copy this down. Okay, so now what I want to do is show you charging by induction happening with the the objects that I had. So this is, for me, very fun. I really enjoy it. Charging by induction, pretty dramatic. And so, almost like, looks like magical, all these things that I'm doing with touching the charge. So what I want you to do before I send you back to look at those demonstrations, I want you first to flip back to your notes and review charging by induction. Review the 4 basic steps so you could understand what's happening and it won't seem so mysterious. So go ahead and do that now. I'll create a pause. All right, so let's have a look. I've got a plastic plate over here. Another metal plate with a plastic handle. And what I'm going to do is I'm going to charge this up by rubbing it with the fur. Nice and charged up. All right, now I put this on here, and let me take it off and go near the electroscope. Nothing. Now watch this. Listen carefully too. Hear that little zap? I take my finger off. Look at that. And if I touch it, you could even hear a spark. Okay? Lots of charge transferred there. So, again, let me show you. Now, in theory, I don't need to recharge this plastic up, but over the years, I find that it loses a little bit. But in theory, it doesn't lose any charge in this process. So, again, listen. You hear that spark? Now I remove my finger and I bring it near, and it made the electroscope spread apart. Now let me touch it to the table, the neutral. Ooh, that was a nice spark, right? Let me do it again. Touch, release, bring it near, and the vein spreads apart. But, ooh, that was another good spark. Let me show you a little subtlety. Okay, touch my finger. I won't let it go. I bring it up like this, and now nothing. Okay, leave my finger intact. Now release it. Nothing. I must touch and release while it's on the plate, the plastic, the charged plastic. And only then does it work. Okay? Okay, so I hope you enjoyed that even 10% as much as I did. Then you would have had fun. All right, so now what I'm going to do is show you what I think will be your favorite slide of the entire presentation. So, are you ready? There we go. The end. So that's it. How we can develop charge. Everything is made of charge. People, food, air, earth, the sun, right? Everything. The way you develop charge is you make an imbalance. You're always pulling electrons off to make something positive or dumping electrons on to make it negative. It's always a transfer of electrons. There's charging by friction, charging by contact, charging by induction, movement of electrons throughout, always, and those are different ways to charge. All right, so I hope you enjoyed. I hope you found it interesting, the information we talked about. I'll see you in the next physics video.